So you can see from this slide that we're going to cover gases today, which is your chapter 13, and there'll be an exam on that. Then we've only got 2 more topics to go. There are 3 topics here, but we're not going to look at energy. There's just not enough time. Besides, energy is not part of the course description, so I can't legally put that in here. Although the topic would be useful for introductory chemistry, it's not absolutely necessary. So we're talking about gases, and then the last 2 topics we have for the semester are acids and bases and redox reactions. Those 2 are pretty much vital for any discussion of chemistry. All right, gases. These are the sections of your chapter. We'll hit those one at a time. The question that always occurs to me when I'm looking at a new topic is, why study the topic? You know, if there's no good reason to study the topic, then why am I wasting energy on it? As a matter of fact, the study of gases is vitally important to understanding how the world works. Real phenomena in the world, an understanding of those phenomena would not be possible without a clear understanding of gases. And of course, the scientific method was being developed at the time that gases were becoming popular among would-be scientists. They called them natural philosophers in those days. In the middle 17th century, we would call them scientists today. And the fundamental breakthroughs in chemistry came because of investigations of how gases behave. Now, there are reasons for that. Gases, the study of gases in the middle 17th century was made possible by the technology that was available at the time. And we're going to talk about some of those technologies here in just a few minutes. But the study of gases were made possible by those technologies, while the studies of liquids and solids would have become more difficult with the state of technology at that time. All right. Got you covered. Now, it's true that through the centuries, alchemists had more or less mastered what they could of the study of liquids and solids. They had no choice because many of them were interested in one of 2 things: either turning lead into gold is the common expression, but transmutation is the fancy word for that. Changing one element into another. And the other holy grail that they were looking for was the elixir of life. You know, some concoction that would prolong human life. But they had discovered several of the elements, and they were not all gases. But when you start to study, when you start to do studies in chemistry in a scientific approach, then gases are your best bet. One of the things about gases that's useful is that a gas has low density, which means that it has very low mass per unit volume. Now, where does that volume come from? The volume comes from the space between the molecules. There's lots of space in a gas. As we might even say, excess space. So what I'm getting at is there's lots of room between the molecules, which means that gases can be treated as if there's no difference from one gas to the other. Nitrogen, oxygen, hydrogen, helium, those gases can be treated as if their identity doesn't matter. A gas is a gas is a gas. And that becomes very useful when you study gases, because many of the properties of gases, you don't have to be particular about what you put in there in your study as a gas. Okay. So gas is one state of matter, and it when it's placed in a container, it expands to fill the container. It doesn't just sit in one corner like a liquid would. Liquid would just sit there no matter what the container. So the gas requires a container for both its volume and its shape. Another interesting phenomena of gases is if you put two or more gases together, they always form a homogeneous mixture. They dissolve in one another. Another word for that is solution. They always form a solution. And a confined gas will exert pressure on the vessel that holds it. If you push more gas into the container, then it will exert more pressure on the inner walls of the container. Now, how do we know that? Well, because if you stick a gauge in a hole in the side of that container, then you can measure that increase in pressure. And there are several things that can increase pressure of a gas. And we're going to, first of all, we've got to define pressure. And then we're going to talk about the laws that define the behavior of gases. So we're going to get there. These are just introductory statements. So what is pressure? Pressure by definition is a force that's applied over a definite area. Okay, so in the English system or the imperial system, force is measured in pounds. So we have an intuition about what a pound is. Like I weigh about 200 pounds, so a pound would be 1/200th of my total weight. And area, typically in English units, is square inches. So pounds per square inch would be one expression of pressure. There's your area, there's your force. And it's important to recognize that pressure is an intensity factor. In other words, when you measure pressure, say inside a vessel, it doesn't matter where you measure that force per unit area. It's going to be the same everywhere. And if you could introduce a measuring device into the center of the vessel, you would also measure that same pressure. It's an intensity factor. It doesn't matter how much you have. What's the total volume? If you measure a pressure of a volume this big, then, and you take a portion of that, you block it off, the pressure is going to be the same, no matter what size or the amount that you have. That's an intensity factor, whereas force would be a capacity factor. The bigger the force, the larger the number, or the larger the area, the larger the number. Okay, we have several ways of expressing pressure in SI units, that is, International System Units. The standard is the Newton, right? Named after Isaac Newton. That's a measure of force. And then the square meter, based upon meter as the standard of length, so the derived unit of area would be the square meter, right? And one of these is equal to 1 Pascal. The Pascal was invented, let's see, here we go, was named for a polymath, they say, a French mathematician and physicist of the 17th century. His name was Blaise Pascal, who experimented with fluid pressures. Now, what's a fluid? A fluid is a word that encompasses both gases and liquids. Actually, anything that flows is a fluid. Gases will flow, they will escape and flow out. Some gases are dense enough that if you pour them out of your container, they'll sink to the floor and move across the floor. And you can see it happening. The liquids are also fluids. Solids are not fluids. So he experimented with gases and liquids and has this unit of pressure named after him. It's important to understand what a Pascal is equal to, newtons per square meter, because if you have to do a calculation that involves any other variables in the calculation, and the variables use newtons or square meters, then you need to understand this relationship so that if necessary, you can combine or cancel units. If you stick to pascals, then you may not recognize that certain units can be canceled or added. Okay. So notice that this is newtons per square meter, not kilograms per square meter. A kilogram is a mass. Now, on the surface of the Earth, the kilogram is going to produce a constant force. So sometimes you will see pressure expressed in kilograms per square meter. Just recognize that kilogram is not a force, even though we use it that way sometimes. Now, another equivalence for Newton. Actually, if we use Newton's second law of motion, which is this. Force is equal to mass times acceleration. So acceleration is what? Acceleration is a change in velocity. So if a velocity is in standard units, meters per second, then a change in meters per second would be meters per second squared. So every second, the velocity changes. So that's why acceleration is meters per second squared. How about mass? Standard is kilograms. Right? So if you have one of these and one of those times each other, just one of them, 1 meter per second squared and 1 kilogram, that is equal to 1 Newton. So that's probably why Newton gets credit and named for the unit, because of his second law. So there's another equivalence. If you enter a calculation where you have meters and seconds and kilograms applied to a force as part of the expression, then you'll know that it's possible to maybe cancel or combine other units. Okay? So we have the standard unit of pressures, the Pascal, but they're convertible with other units of pressure expression. Now, the one that we're going to be, one of the units of measure that we're going to be using in this class, in this chapter, is the atmosphere. Right? 1 atmosphere is the pressure that, the average pressure that you would experience at sea level on the surface of the earth. Now, of course, that changes, but it's been standardized over time. And now the accepted value is equated to pascals as 1 atmosphere equals 101,325 pascals. Or you'll often see kilopascals, right? 1,000 times a pascal. So in that case, 1 atmosphere would equal to 101.325 kilopascals. Right? There are other equivalents. Right? 1 atmosphere can also be equal to 760 millimeters of mercury. Now, that doesn't mean anything right now because we haven't said, how do we derive that? I mean, where did that come from? Right? I'm going to show you in just a minute. But this is also equal to 760 torr. Right? What's a torr? A torr is 1 millimeter of mercury. And the torr is a unit that was created to honor the inventor of the barometer. Evangelista Torricelli was an Italian mathematician and physicist who invented the device in the middle of the 17th century. 1643, maybe 1644, we're not exactly sure. But it was this invention that allowed scientists to quantify pressure of a gas. Okay, so let's look at that invention. All of these equivalents, right? 1 atmosphere is this, so that means this is also equal to that, and that's equal to that. You know, they're interchangeable. You have these equivalences, and remember, whenever you have an equivalence, you have a conversion factor. All right, so here's what Torricelli's barometer might look like. It probably didn't look exactly like that. But what Torricelli did was, I mentioned technology earlier. One technology that medieval and early modern craftsmen had mastered was the ability to produce glass tubing of uniform diameter. They knew how to do that. So Torricelli obtained for himself a length of glass tubing and closed it off at one end. Right? So then he tipped it up, open end up, see if we can get back on. There we go. Open end up, and he filled it with mercury. Now, why did he use mercury? He could have used water, right? But water has a certain volatility. So he could put the water in there and it would immediately start to evaporate. And so he couldn't be sure of its of how much water he put in there. The other reason he used mercury was density, right? Mercury is about, if memory serves, about 13.5 grams per cubic centimeter. Compare that to water. Water is just 1 gram per cubic centimeter. So mercury is 13.5 times as dense as water, which means that he could use a short tube. If he used water, he'd need a tube 33, 34 feet long. That would be a little stretching technology a bit. So he used mercury. Mercury is a metal, but it's also the only liquid metal at room temperature. And it has very low volatility. So once he put the mercury in there, he knew it was going to stay. Okay, so he filled it up with mercury. Then what did he do? Well, he had a bowl of mercury here. And he put his thumb, his bare thumb, over the filled tube, right up to the very rim, and inverted it and submerged his hand in the mercury, and then turned it loose, let loose with his thumb. Right? So the mercury that was up here in the top, he noticed that it sank down to a given level. And then it stopped. Right? So what's holding it up there? I mean, you can't claim suction because there's nothing up here. Right? There's no pressure up there. And suction is kind of the opposite of pressure. So what's holding it up there? Torricelli reasoned that what's holding that column of mercury up is, since there's no pressure on it from this side, there's pressure on this side pushing against that pool of mercury, and the forces being transferred through the mercury up through the column to hold that column of mercury up. So the force is sufficient, column of air in the atmosphere pushing down on the mercury to hold that column up. So he found a way to measure the forces of atmosphere. Now, this says 760 millimeters of mercury. That would be the standard for 1 atmosphere. But suppose Torricelli did his work at some elevation above sea level, which he probably did. Then it would be a little bit less than that, because why? There's less atmosphere above the pool to push down on it. All depends on altitude. But if you went down to sea level, then the height of the mercury column, and the height here is measured from the surface of the pool to the height of the column. So if the tube moved down a little bit or up a little bit, it's still submerged, then the position of this column of mercury would change in the glass. It would apparently change, but the length of the column would remain constant. In other words, from that level here up to this level would be the same. So if it goes down to sea level, it's going to be near 760 millimeters. But what if he took his barometer and put it in the back of an ox cart and went up a mountain, which he did? He noticed that the height of the column decreased. And he reasoned that that was because there was less atmosphere above him to push down on the pool of mercury. So now we had a way of measuring pressure. In the beginning, it was just air pressure, right? And some scientists use that to measure air pressure over a period of time. So they just set the barometer on the bench and just watch it. And they noticed that the level of mercury went up and down. And they correlated that change in mercury level with changes in weather. So as the weather started to get bad, stormy, they noticed that the column of mercury decreased. Low pressure, that we now call low air pressure or low atmospheric pressure. And they noticed when the weather started to clear, got better, the mercury level rose. Higher pressure. And we still correlate high pressure and low pressure with different types of weather to this day. But that's not the only use that you can, that's not the only use for this technology. A question comes to mind for me. How could Torricelli be sure he was measuring pressure and intensity property and not just total force? Right? What if Torricelli had expanded his pool of mercury? Right? Just made it bigger with the same tube. What would happen to the column of mercury? Stays the same. Exactly the same. So while the total force of atmosphere might increase with increased area, the intensity property, that is pressure, did not change because that total force is now spread over a larger area of this surface area here. Okay, so he knew he was measuring pressure, force per unit area. Now, what other uses could we this technology, as Torricelli invented it, is a barometer. Meter meaning measure, baro meaning atmosphere. He measured the atmosphere. But what if you use that similar concept and you say, let's change things around a little bit here. Let's say the tube now is submerged in mercury. Right? Like that. And you've got a certain level up here. Actually, it's going to be convex. But suppose we enclose this space above here. Right there. And we have a tube that's attached to a cylinder of gas or a sphere of gas or some container. And you put gas in there and it pushes on the surface here. And if you have more gas in here, then it'll push harder. You say pump more gas into it. And you can measure the pressure inside that container. Okay? The other possibility is you're open at both ends. One end leads to the gas contained in this sphere, and then the other end is atmospheric pressure pushing down. So the difference in this height to here is a measure of what? It's a measure of the oppositional pressure of this gas versus atmosphere. Right? So if you do that, and we look at this figure here, if you do that, and the pressure inside the cylinder is less than atmospheric pressure, then the difference in height is going to show that this side is lower than this side because there's less pressure in here opposing atmospheric pressure. But if the pressure inside the vessel is higher than atmospheric pressure, you'll see just the opposite. This level is going to be lower, and this one's going to be higher against atmospheric pressure. All right, so we can see that this height difference is an oppositional measure. So what's the pressure inside the vessel? Let's say there's the pressure inside the vessel, and then there's this measurement of pressure. Hold on a second. The manometer, that's what that's called, a manometer pressure. And then there's atmospheric pressure. Let's see, let's call this gas pressure. Okay, how are they related? Well, if we take the pressure in here and subtract the pressure on the outside, we should get the pressure here. Or the pressure of the gas inside is actually this manometer pressure plus atmospheric pressure. Right? What pressure is being exerted against the gas? The gas is pushing this way, and atmosphere is pushing this way, and mercury column is pushing that way. So you get this one plus that one has to oppose this one, right? So how do we know what the pressure is in here? Suppose we can't measure it. We could, but let's just, for argument's sake, say we can't measure it. If you know the atmospheric pressure and you measure the height of that column, then the pressure of the gas inside the vessel is the summation of both of them. So what do you need? Well, you need a barometer, a separate barometer to measure atmospheric pressure. And then you add that to this one. Okay. Now there's another type of manometer that health professionals use day in and day out. It's called the Stigma Manometer. The common name for that is a blood pressure cuff. You wrap it around your arm, pump it up, and the opposing pressure that you're measuring is the force of your blood pressure pushing against that bladder. Okay, and that way you can measure the blood pressure at this location without having to stick a needle in there and measure it directly. But those values that you get for systolic and diastolic pressure, right? Say, if it's 120/80, what does that mean? That means millimeters of mercury. Right? That's what those numbers are. Each one is millimeters of mercury. Right? This is the systolic pressure when the aorta contracts, makes the highest pressure here, and then after it relaxes, that's the pressure that's left over inside your vascular system. So high, low. And of course, in order to determine when those are, typically what you would do, if you did it manually, right, not using one of these fancy machines, you would have a stethoscope and you would listen to listen for the Korotkov sounds. right? I think there are 5 of them. Changes in the way you hear the blood flowing in here. And 2 particular Korotkov sounds tell you when this one starts, as you pump it up and let the pressure out, let the air pressure out of the bladder, you would hear one sound here and then the other one here. And that would tell you, as you're reading the meter, that would tell you the high and the low pressure. Okay. So, and there are other ways to demonstrate the existence of air pressure, right? We don't feel air pressure, right? I don't feel it. Why? Because the pressure inside my body is the same as the pressure outside. There's no difference, right? And that's typical in the sciences. Measuring absolutes is rare. Most often we measure differences, right? Change in color, change in height, change in mass, various types of changes is what we're keyed in sciences to measure. In this case, this collapsing can, my father used to do this when he was a teacher, and he taught earth science to 8th grade students. And this would always get this is one of those ooh-ah moments. You take a can, like this one, empty solvent can, and you put a little bit of water in it, and you heat it up and boil the water. So what's going to happen? Well, when the water vaporizes, what does it do? It fills the can. It expels all the atmospheric gases from the can and replaces them with steam. Right? Once you've established that, then you just plug the hole. Either put the cap on. It's probably easier to plug it with a stopper. And you turn the heat off. So now what's going to happen? Well, the gas that was filling that area at 100 degrees Celsius, now as it cools, condenses. Right? So what do you have in that can when the water condenses? Well, all the space that's not occupied by the water anymore is a vacuum. Right? So there's no gas. That's what vacuum means. There's nothing there to push against the inside walls of the container. So the outside walls are still experiencing atmospheric pressure. Right? Before, you had pressure on the inside and outside because the hole's open. So nothing's going to happen. Right? But if you remove gas from that space, then the outside pressure is unbalanced and it crushes the can. Oh, by the way, when Torricelli invented his barometer here, that space right there was the first vacuum. Empty space, nothing there. Okay, so that demonstrates the reality of air pressure. So let's do some conversions, right? You're not always going to be given pressure values in terms that you can use, right? So you need to be able to convert them from one pressure to the other. By the way, before I go any further, when we describe a gas, to fully describe a gas without saying what kind of gas it is, like oxygen, nitrogen, so forth, you know, that we're not talking about that. We're saying just a gas. To fully describe the physical characteristics of a gas, you need 4 terms. You need to know the pressure of the gas. You need to know its volume. Right? You need to know the temperature. And you need to know how much of it is there. N stands for moles. Right? How many particles of gas are there in moles? So if you know those 4 terms, you can completely describe a gas without saying what kind of gas it is. Right? you need to know the element. If you want to talk about the gas in terms of its reactivity, then you need to know the element. But if you don't know the element, then you can still describe the gas in those four terms. All right, so let's get back to the problem here. The pressure of a gas, say, is measured at 2.5 atmospheres. What would be the value in terms of torr, and then converted to pascals? So where are we headed? Well, we're headed to different units of measure, right? Torr or pascals. That's what we know. So we need an equivalent statement so that we can use a conversion factor. All right, so if we have 2.5 atmospheres, and we want to convert that to torr, we need a conversion factor that will give us torr on top in the numerator and the atmospheres in the bottom to cancel. Okay, what's the relationship between torr and atmospheres? Well, we said on an earlier slide, 760 torr is 1 atmosphere. So now you can convert from atmospheres to torr. All right, and that's 1.9 times 10 to the third torr, or 1900 torr. All right, so what else can we say about that? I mean, it's not one of the questions, but we can say that's also 1900 millimeters of mercury. How about pascals? Right? What's the relationship of atmospheres to pascals? Right? 1 atmosphere equals 101,325 pascals. So it's simply dimensional analysis. What dimensions do you start with? What do you want to end with? Then how do you get there? What conversion factor or factors do you need? All right, let's go the other direction. Say we measure the pressure, the vapor pressure over a beaker of hot water is measured as 656 torr. We're not going to say how we did it, right? That's another 20 or 30 minutes worth of discussion. Let's say we've measured it at this many torr. What is this pressure in atmospheres? Right? So you just say, now we have a different need. 656 torr. Now the torr has to be on the bottom and atmospheres on the top to give us atmospheres as our answer, right? So 760 here divided into 656. Right? So it's not going to be 1.16. That's more than an atmosphere, and this is less than 1 atmosphere, right? So it has to be B, C, or D. Well, let's see if we can. What's 6 divided by 7? Right, that's more than a half, right? So it can't be a half. So it's either B or C. So which one is it closer to? Yeah, guess. B. Yeah, good guess. So B is the answer. All right. Okay. So now we're going to talk about gas laws. Right, remember the difference between a law and a theory. A law simply states what happens. Under these certain circumstances, you will always get this answer. That's what a law says. And the first gas law was derived by experiments done by Robert Boyle, who was an Englishman. He was interested for maybe for several reasons, but for one reason for sure is he was limited by the technology. He couldn't investigate other aspects of gases other than pressure and volume. Pressure and volume, they had the barometer by now, and they've always had the volume. So he wanted to investigate what's the relationship between pressure and volume. Well, he knew from preliminary experiments that if he did not hold this one constant and that one constant, then he could not investigate these two. So for Boyle, temperature and moles must be constant. Right? You can't change the number of moles of gas, and you can't allow the temperature to change, which is really not a tall order. And I'll show you that based on Boyle's experiments. So he investigated the relationship between pressure and volume. Right? And remember, the technology for uniform diameter glass tubing was pre-existing. He just changed the shape of the tube. Right? He used a J tube. Right? Looks like a J. Right? Yeah, looks like a J. I was just checking. I don't write J a lot. This end is closed and this end is open. So how did he come to this situation? Well, his J tube, shaped like this, right? That's really not uniform diameter, but use your imagination. So he says, empty tube. What does it have in it? Well, it's got atmosphere. It's got gas. So he added mercury. And it started to pool at the bottom. Right? It's still open to the atmosphere, right? So he hadn't got there yet. So he eventually put enough mercury in there that it touched the inside wall. And when it did that, this gas was trapped. That established constant number of moles. Once you trap the gas in there, then there's no change in it. It's got the same number of moles, same amount of gas in there every time. Okay, what did you do about temperature? Well, in England, temperature can change like anywhere else on the planet. But the experiment didn't last months and years. It lasted minutes. Right? And over a minute's time, the temperature is not going to change. What if it did? How would you stabilize the temperature? Well, one way you could do it was find some type of environment that was constant, right? You know, carry your J tube into a cellar, into the basement, right? Underground, where the temperature is relatively constant. Or just submerge it in an ice bath, and the temperature will always be 0 degrees. Right? And that's probably why standard temperature for gases, now this is gases only, standard temperature for gases, STP, standard temperature is 0 degrees centigrade. Standard pressure is 1 atmosphere. Now that's for gases. If you talk about any other type of chemical reaction, the standard temperature is 25 degrees Celsius. But when you're doing gas experiments like this, the standard is 0 degrees. And that may have been where it came from. They knew that when you put water and ice together, as long as they're both there together, the temperature is constant at 0 degrees. Okay, so what did Boyle do? Well, he noticed that when he added more mercury in the beginning, they were pretty close together, the heights. But as he added more mercury, say he came up here, there was a difference in heights. So he reasoned that what he was measuring was the oppositional pressure of the gas trapped in that short length of J tube. And he could equate the volume inside the J tube with the length, right? That distance between here and here could be equated to volume. He could calculate the volume, right? Because what did I say? Uniform diameter tube was very easy to make. They knew how to do it. So what do you need to know the volume? Well, the volume is height times area, right, of a cylinder. The cylinder has a certain area times height is its volume. So what's the area? Well, it's pi r squared or it's pi d squared over 4. So they knew that a uniform diameter, they could calculate the area if they wanted to and determine what the volume was inside that trapped section. Okay. So that's everything I've told you in writing. So the pressure on that gas is what? A combination of this height plus atmospheric pressure. The total pressure on the gas is the combination of the height of this mercury plus the pressure of the atmosphere. So Boyle would need a barometer separate to measure the atmospheric pressure. Then he would add it to the height, and then we'd know the total pressure on the gas. And the relationship between pressure and volume, you'll notice as the pressure increases, see, if you go from here to here, what happens to the volume? The volume decreases. Right? So he just created a table. Pressure, volume. And he had values here. You know, like the pressure maybe is only 10 millimeters of mercury. Then he goes to 20, and then 30, and then 40, and 50. So that as the pressure increased, of course, that wouldn't be total atmospheric because you'd have to add 760 to it. But as long as the atmospheric pressure doesn't change, then the relationship still holds, right? Because if you say this is that plus atmospheric, right, on down, then you notice the volume was something, right? So if you measured volume and length, the volume might be 10 millimeters. Now let's make it bigger than that. Let's say it's 100 millimeters long. The length represents the volume. 10 times that would be 1,000. Then he noticed that if he increased it to 20, if he added mercury until the difference was 20, then he noticed that the length of the gas pocket is now 50. And then if we went here, and then he went here, and then he went here, there. He noticed that pressure times volume is a constant. That, in its simplest form, is Boyle's law. Pressure times volume equals a constant. Now, that constant will change depending on these other conditions, like how much gas is trapped, what's the temperature. So the K is constant for that individual experiment, but the K is not constant worldwide. But it's a beginning. That's where he started, determined that this is the relationship. So how would that look if we well, let's see, the next page has a table. There we go. So if we have these values, right, measured in an experiment, and this came straight out of your book, the actual measurement was the product of those two measurements with these values. And to three significant figures, they're pretty close. Right? There's experimental error in there, right? We talked about that very early on. Every measurement has some error. Right? So this is hypothetical. That looks perfect, but it's really not that way when you do the measurements. Okay, so this is Boyle's law. Simply stated, it just means pressure times volume is a constant. Now, let's say we want to visualize that. Let's plot the data, right? You got, you're changing the pressure, so that's the independent variable. That'll be on the x-axis. Right? The independent variable always goes on the x-axis. The y-axis is the dependent variable. The volume changes as the experimental meter changes the pressure. So this would be the volume. So what would that look like? Well, for low pressure, you have high volume. Right? For a high pressure, you have low volume. And then you have intermediate in between here. Makes a curve, right? It's a special kind of curve, actually. It's called a hyperbola. Not hyperbole. Hyperbole is a literary term, exaggeration for effect. This is hyperbola. It's a mathematical term. So what is a hyperbola? Well, one characteristic of this hyperbola is that these tails out here, there and there, will never touch the axis. They'll get smaller and smaller and smaller, but they'll never touch it. Okay. So what else do we know? Well, there's another term for that. It's called an inverse relationship. Anytime you get two variables in a product times each other, and they're equal to a constant, then those variables are inversely related. And it stands to reason. If this is going to stay constant, then if that one goes up, this one has to go down. If it goes up as the same as this one does, then you get this one being bigger and it's not constant anymore, right? So if this one goes up, that one goes down, or as this one goes down, that one has to go up. That's an inverse relationship. Every time you have a product equal to a constant, that's an inverse relationship. Okay, in this case, the slope is from upper left to lower right, right, that way. And in mathematical terms, that's called a negative slope. What would be a positive slope? Positive slope would be the other way, this way. This slope, negative slope, is inverse relationship. Positive slope would be a direct relationship, right? Because as this one goes up, this one also goes up. So it goes up, 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 up. But this one goes like that. So as this one goes down, that one's going up. Right? Negative slopes always mean inverse relationship. Positive slopes mean direct relationship. Okay. Now, this is the statement of Boyle's law, but it's not very useful, right? Because if any of the conditions change in the experiment, particularly temperature and moles, then that's not constant anymore. It's a different constant. So we need a way to express Boyle's law that's more useful. And I call this the before-after scenario. The before-after problem is simply stated. What are the conditions before you change something? So what's the pressure when you start? There. What's the volume when you start? That's equal to a constant, is it not? Boyle's law says it is. So if you're given conditions at the beginning of the experiment, before anything changes, that's it. After something changes, what is it? Now you've got new conditions, but they're based upon the original conditions. In other words, we take this one, we change something. Now we get these new values, a new pressure and a new volume, right? But they're equal to the same K, right? As long as these are the only conditions changed, they're equal to that same K. So if this is equal to K and that's equal to K, those two are equal to each other. Okay? That's why P1V1 equals P2V2. Or another way of saying it is P sub I times V sub I, initial conditions, equals PF, P sub F, times V sub F, final conditions. So initial conditions here might be 1 atmosphere pressure and a volume of 1 liter. And notice the temperature doesn't change. And of course, the number of moles can't change because this is a sealed container, right? So if the initial conditions are 1 atmosphere and 1 liter, then what happens if you increase the pressure on that same vessel to 2 atmospheres? Well, in order to be constant, 1 times 1 is 1, 2 times 0.5 volume is equal to 1, or 4 times 0.25 is equal to 1. See, that's before and after. This is before, this is one after, and this is a second after. So let's look at it in those terms. Suppose you have a sample of helium gas, right? Now we're saying what it is. It really doesn't matter because you're not going to change the helium gas in the experiment anyway. But you have this sample that occupies 12.4 liters. So when you're using this scenario before and after, it's important to get your numbers in the right place. So let's say we have initial and then final. What's the initial volume? 12.4 liters, correct? And the temperature is 23 degrees centigrade, Celsius, doesn't change. And with this volume, you have 0.956 pressure, atmosphere. Initial conditions. What volume, that's the question, what volume will it occupy at 1.2 atmospheres? So the new pressure is 1.2 atmospheres. And the new volume is the question. Okay? When you take a word problem like that and put it up here on the board like this, then you're less likely to make a mistake, because now you're assigning those values where they need to be. Initial, final. If you put them in the wrong place, then you get the wrong answer. So how would we express this? Well, PI times VI equals PF times VF. And we're solving for this one, right? So VF equals these two divided by that one. You just plug the numbers in. Now that's the hard part. That's the thinking part. Plug the numbers in and crunch. Okay? Or you can plug the numbers in first and then solve for the unknown. Either way, I mean, it works both ways. All right, there you go. V2 is the final volume at 9.88 liters. Okay. Does that make sense? Notice, if you're changing the pressure from a low number to a high number, then the volume should be from a high to a low. So you're going from low to high, high to low. That makes sense. All right. Let me check my time here to be sure I'm not running out. 11:50. Okay, we're good. All right. Now we're moving ahead several decades. And we come to a Frenchman named Charles. That's his last name, not his first name. Charles' law. For Charles' law, we need to hold, this is constant, and this is constant. And the relationship between volume and temperature is investigated now. So pressure has to be constant, moles has to be constant. And we want to know the relationship between volume and temperature. What happens to the volume if you change the temperature? Well, Charles noticed that if you change the temperature, right, on the x-axis, that the volume of the gas increases, right? What kind of slope is that? The slope is positive, which means it's a direct relationship. Direct relationship is not product of variables, but quotient of variables. That's Charles' law, volume divided by temperature. Now, the thing about this is you get a different slope for different gases, which is really not a problem, because once you've confined the gas, number of moles, then you're not going to change it anyway. All right, so that's everything in writing that I just told you. All right, here's the problem. What if your temperature goes negative? What happens to your relationship? It's all messed up. If you got negative numbers in here, then the calculation can't hold for a constant value. Temperature has to be all positive values forever. So that's why temperature, we cannot use, we can plot the data like we did previously, right here. We can plot the data, but we can't do the calculation unless the temperature is in absolute terms. So the conversion for temperature, remember, is if you want to know Kelvin, you take degrees Celsius plus 273. And whenever you're working with temperature, actually not just with gases, but everywhere else, you need to convert it to an absolute value, which in this case would be Kelvin. Now when you do Kelvin, you've got positive values of temperature always. Why? Because Kelvin is reference to 0 degrees. Nothing below it. Can't be anything below it. Absolute 0. Let's see. I think I've done that discussion before on where Kelvin was derived. Maybe I'll do it again just for completeness. So what Lord Kelvin noticed was that for gases, if we have our degree C here, and we have volume here, he noticed that you could plot a straight line down to a point. These are actual values that he would plot for a gas. But the experiment wasn't carried any lower than that. Or maybe it went down to here, right? Negative temperatures. This is 0. But if he extended that line, a fancy word for that is extrapolation. He extrapolated the line out to here. So what does that mean in real terms? That means if you go down to this temperature on this scale, you get 0 volume, right? That would be considering an ideal gas. An ideal gas stays a gas all the way down to absolute 0. And he noticed that this temperature was minus 273.15 degrees C. And he said, oh, here's what I'm going to do. I'm going to invent a new temperature scale. That's 0 now on my scale. So 0 degrees Celsius now would be 273 K. All right. So the long and the short of this story is always convert temperature to Kelvin. All right. So when we do that, we notice that all of these gases converge. They may have different slopes here in measured regions, but they all converge on absolute zero. Okay. Let's see. You know, actually, Charles did much of the beginning work on the relationship between volume and temperature, but he didn't publish it. It was published by this fellow, Lussac, you know, about 25 years later. But Lussac apparently was an honorable man, and he gave Charles credit for it. So that's why it was called Charles' law and not Lussac law. Okay. Let's see. Yeah, you can write it that way. Instead of writing it like this, you can write it like this. Okay. Now, why would we want to write it like that? Because what does that look like? Remember the generic straight line formula? Y equals mx plus b. There's the volume. There's the temperature. There's the constant, the slope of the line, and there's the y-intercept. If we use temperature as Kelvin, then that value is always going to be 0. The y-intercept will be 0. So, and scientists love straight lines. Straight lines are so much easier to deal with. But it is a direct proportion, no doubt about it. Now, we can use the same line of reasoning for Charles' law as we did for Boyle's law for before-after scenario problem solving. So if this is one set of circumstances equal to the same constant, if we change the volume or the temperature, then they're still equal to that same constant, means they're equal to each other. So this is the before-after for Charles' law. V1 over T1 equals V2 over T2. Now, why did Charles' law, experiments not occur until the late 18th century? Well, it had everything to do with technology. They didn't have a reliable way to measure temperature. There were various propositions over time, but a reliable thermometer wasn't invented until just before Charles did his work. So now that he knows how to measure temperature accurately, and the temperature scale was invented, then the experiments, logically speaking, the experiments were doable. All right. So what do we do when we have a balloon that contains 1.3 liters of gas at 24.7 degrees Celsius, and then we submerge that balloon in liquid nitrogen. What's the new temperature? Eventually, the temperature gets down to minus 195. And the question is, what's the new volume? Right? Pressure hasn't changed, right? Still atmospheric pressure on that balloon. Notice here we have a negative value for temperature. So if we try to use the formula, we're going to end up with a negative volume. and that just won't do. We can't have a negative volume. So these temperatures have to be changed to Kelvin. And we're using 273, leave off the decimals. For our purposes, 273 is good enough. Right? So this one's going to be what? There. 3, 7, 9. K. Notice there's no degree mark with K. It's just number K. How about this one? Let's see if I can do that in my head. $78 K. Okay, now to solve the problem, there's your formula. Plug the values in, right? There's your unknown. V2 in this case is final volume, and solve for it. And you get 0.341 liters. Does that make sense? Well, they're directly related, correct? Volume and temperature. If we go decrease volume, if we decrease temperature from here to here, then the volume decreases from there to there. So yeah, it follows the correct trend. All right. Now, one more law. Avogadro's law, another Italian. I'm going to flip pages on my hard copy. Helps me stay focused. All right. Now we're into the 19th century. Well, what Avogadro noticed, actually, what Avogadro said was this. You have two containers filled with gas. They're equal volumes. This one is equal to that one. Equal volumes. They're also equal temperature. And we measure equal pressure. Right? Now, what also has to be equal, if these conditions are the same, what also has to be equal is the number of particles, the number of moles of gas in each container is exactly the same. Right? That doesn't, the mass may be different, but the number of particles, the number of molecules, the number of atoms in each, actually the number of molecules, is the same. That's what Avogadro said. He got credit for the expression of the law because there were scientists after him with integrity that gave him credit for the original idea. So with this information, a statement of Avogadro's law says that if you, at constant pressure, right, here are 4 terms. We still got constant pressure. And now we have constant temperature. We're going to relate these two. If we put more moles of gas into the container, then the volume will increase. Right? So if we add more moles, then the volume has to increase to make that constant. Or we could write it this way. Oops. Like a straight line. It's a positive slope. All right. Okay, so that it's a ratio, so it works upside down or right side up. And this is the before-after scenario. Right? The ratio of the original number of moles to the volume is equal to the new number of moles to the new volume. That's a direct proportion. Okay? Let's see, let me scoot this back over a little bit. There we go. All right. So, before situation, 2.45 moles of argon gas. So this is the original moles, initial, 2.45 moles. What's the initial volume? 89 liters. What will the volume be if we change the number of moles to 2.10 moles of argon? And the pressure is constant. But we allow the volume to change. Right? It's like in a balloon or in a cylinder with a frictionless piston on top. So it will be the new volume. Well, we would expect that if the number of moles decreased, the volume would decrease. And solving the problem tells us exactly that. 76.3 liters is the new volume. All right, before we get to the ideal gas law, I want to introduce the combined gas law. Okay, we're going to say this. Something is equal to something else. We know that pressure times volume is related like that. We also know that volume and temperature are related like this. Right here, there, and there. So if pressure is held constant, then the pressure terms cancel because they're equal, right? So they cancel, and we're left with Charles' law. But volume and moles is also related like that. Right? So if we hold pressure and temperature constant on both sides, they cancel. And that leaves us with volume and moles relationship. This is the combined gas law. And it's in the form of before, after. So this way, you can know several different conditions, right? If you know all of these to begin with, and then you know all of these but one, let's just say we don't know the volume, right? You change the pressure, moles, temperature from these to these, then you can calculate the volume. With this equation, you don't have to hold everything constant. You just need an equation with one unknown, and you can solve it. Okay, so now to the ideal gas law. What do we mean by ideal? Right. Well, I mentioned one earlier. One condition of an ideal gas is that it stays a gas, always and forever, no matter what the conditions. You can cool it down, put pressure on it, and cool it down to absolute zero, and it's still a gas, right down to the point it disappears. Right? We know that's not true. Right? Gases, if compressed and cooled, will eventually become liquid and then even solid sometimes, like carbon dioxide. Carbon dioxide will eventually become a solid, which is known by another name called dry ice. Solid carbon dioxide is dry ice. So we know that ideal gas is hypothetical, theoretical, but it's useful. So how do we derive this ideal gas law? Let's see. Let's look at the rest of this slide. Now, how did we come up with that equation? Well, if we look at this, remember how we derived this before and after relationship before? That's equal to a constant. This is equal to the same constant. So instead of putting that out there, let's put a constant out here. That's equal to a constant. Okay? Now, if we fix the units of measure for each of our variables, then that constant can be calculated. Pressure standard is 1 atmosphere, correct? 1 atmosphere. Volume standard is 0 degrees, which will be 273 K. Oops, sorry. Put it in the wrong place. 273 K for that one. And 1 mole is the standard. Now, all we have to do is confine a gas under these conditions, 1 atmosphere, 1 mole, 273 degrees, 273 K, and measure the volume. The volume under these circumstances happens to be 22.4 liters. Okay. Now that we know all of these conditions, these are the values for those conditions, solve for that one, and we get 0.08206 liter atmospheres per mole K. All right, and we give this a special variable. This is equal to R. R is recognized as the ideal gas constant. Now, notice, if you measure these any other way, if you change the units of measure here and consequently the values that go with them, then this constant is different. So it's important that if you use this equation, right, this is now equal to R. And we solve it like this. If you use any other units than these units, then that R is different. Okay? But for these units, that's the value. Now, what's the advantage of this? Well, if we pick the right units, then we don't have to know before and after. This would be the state of the system. So we can use this formula if we know 3 of those values, 1, 2, 3, 4 variables. If we know 3 of them, and that one's constant, and we use the right units of measure, then we don't have to know how it got there. It's just present state. So when you're looking at a gas problem, ask yourself, is this a before-after type? Or is this a state problem? So you look, automobile tire at 23 degrees centigrade, Celsius, with an internal volume of 25 liters, fill it with air to a pressure of 3.18 atmospheres. How many moles of air are in the tire? Right? I don't see any pairings of temperature or volume or pressure. They're just single values. That is a state problem. So we can use that equation to solve the problem. Right? We're going to rearrange it because the question is moles. And then we're going to put the values in. There's atmospheres, there's liters, there's your constant, and there's your conversion of Celsius to K. Solve the problem. 3.27 moles of gas are in that tire. Okay. Let's see where we're going to go from here. So how about this one? Now we want to know the pressure. We want to know this one. Is this a before and after or a state problem? Looks to me like it's a state problem because you're only given single values for each one of the variables. So you have this one, 304 liters. You have this one that needs to be converted to Kelvin. How about 5.670 kilograms of helium? That's mass, that's not moles. Can we convert it though? Yeah, we know how to convert mass to moles. Molar mass of helium, which is rounded off 4.00. Well, that's kilograms, correct? We need grams. 5.670 times 10 to the third grams, right? Remember, kilo means 1,000 times. So there's your kilo right there. Right there, kilograms. You got grams here, moles on top. This is 4. Divide 4 into that. Now you have the number of moles. And we got the constant. We can solve for the pressure. Right? So here it is all in one formula. Right? Here's the number of moles. right? Convert kilograms to grams, and then divide it by the molar mass of helium. There's your R value. There's your converted temperature. There's your volume. Crunch the numbers. "114 atmospheres inside that tank." That is a lot of pressure, a huge amount of pressure. I hope that tank has very thick walls. Okay. Now we've got, we're not done with gas laws yet. Remember at one time we talked about John Dalton and his atomic theory. Okay, that's not everything that Dalton did. Okay, am I getting ahead of myself? Yeah, I'm one slide ahead of myself. Sorry. So in this case, we're solving for temperature. At what temperature? In degrees Celsius. Right? We have to work the problem in Kelvin. But if Celsius is required as an answer, what do? Well, if you get the degrees Kelvin, you just subtract 273. And that gives you Celsius. Right? It's not that difficult. You just have to remember details. So let's see, what kind of problem is this? At what temperature does 121 milliliters of CO2 at 27 degrees Celsius and 105 atmosphere occupy a volume of 2.9? Okay. What type of problem is this? This is before and after. So that means we have an initial pressure, volume, temperature, moles, pressure, volume, temperature, moles. Initial, 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 initial. Final, 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 final. All right. What's the initial pressure? 1.05 atmospheres. What's the final pressure? We're going from 105 to 1.40 atmospheres. By the way, when you're doing these before-after problems, you don't have to change the pressure or the volume units because they're ratioed. They will cancel. The only one you have to change is temperature. And moles, of course, is moles, right? There's no change in that. All right, initial volume, 121 milliliters. Okay? What's the final volume? 293 milliliters. Right? We don't have to change that volume to liters because this is before and after. If you use the state solution, you do need to change to liters. All right, more information. Initial temperature is 27 degrees. We do need to change the temperature. And the final temperature is the question. But it needs to be in degrees C. Okay, what else do we have? Moles. Do the moles change? No. We've got carbon dioxide confined in this volume, right? We didn't change the moles. So the moles are constant. Okay, what's our before and after? Pi Vi over Ni Ti equals final right? Moles is constant, so it drops out. They cancel. So now we just have to plug in values that we know here. We know all three of these. And we know two of these and solve for this one. Okay? There we go. So we plug in the values and we write them this way so we be sure and put them in the right place. And then we solve for that temperature. Turns out it's 969 K minus 273 to give us degrees Celsius. 696 degrees Celsius. Okay? All right, now we can talk about John Dalton. Now, up to this point, we've only talked about laws, and we're still talking about laws. We haven't attempted to explain why things happen the way they do. John Dalton came up with this law in the beginning of the 19th century. And what he said was, if you have a container that has several different gases mixed together, right? They'll be in a solution, they'll be homogeneous mixture. But that's important. The total pressure in that container that you measure is equal to the individual contributions to pressure of each of the gases. So if we could measure individual pressures of each one, you just add them together. Out to however many gases you have. Doesn't matter. Just take all of them. That's the law of partial pressures. The total pressure is equal to the sum of the partial pressures of each of the gases. So, why are these pressures different anyway? If you have different gases in here, say one of them is nitrogen, one of them is oxygen, and the third one is argon. Let's say we just have three. Let's keep it simple. Why are these pressures different? Remember, you get a variation in pressure if you change the number of moles. That's another thing I didn't point out about the combined gas law. Now that we know this relationship, we've got Boyle's law, we've got Charles' law, we've got Avogadro's law, but put them all together, you can also create a law for pressure and moles. The pressure in the vessel is due to, all other things being constant, is due to the number of moles of gas. Increase the number of moles, you increase the pressure. if the others are constant. So these are all related to a change in the number of moles. All right. So in this scenario, well, in this one we have hydrogen, helium, and neon. That's okay. I think those are picked because they don't react with one another. If you have 1.75 moles of helium under 8.4 atmospheres at 20 degrees Celsius, you have a volume of 5 liters. Right? Well, you can also have 5 liters under these conditions if instead of all helium, you have some hydrogen and neon. But the total moles is still 1.75. And this will be total. So the relationship between pressure is based on the relationship between moles, the numbers. So the individual pressures may vary, but if the total moles is the same, the total pressure is the same. That's what this whole picture is trying to explain. We can say this because the volume of the individual molecules doesn't matter that much. There's all this extra space. There's huge amounts of space in a gas compared to the size of the molecules. That makes the distance between them very large. Most of gas is an empty space. So when you compress that empty space, the particles don't get in the way. All right. So what's the practical importance of Dalton's partial pressure to a researcher? Let's see. I missed a slide somehow. Let me back up. Yep, I'm missing a slide. Okay. Or did I put it someplace else? I bet I moved it someplace else, so I'm not going to fret about it right now. All right, so now let's go to a practical example. Suppose that we have a chemical reaction and it involves gases as a product. Doesn't have to be gases as reactants, but gas as a product, and we want to capture the gas. We are proposing that the reaction produces only one type of gas. Say zinc metal plus hydrochloric acid produces zinc chloride, which would be 2 here, plus hydrogen gas. Okay, so let's balance that. There, now it's balanced. So notice that the product here is gas, hydrogen gas. All right, we want to measure how much hydrogen gas we have collected out of this reaction. Okay, this is a different reaction. Potassium chlorate is heated and it decomposes. Let's see, that's not balanced yet. Now that's balanced. So in this case, we're collecting oxygen gas. In this case, we collect hydrogen gas. They're two separate reactions. So for this example, we'll focus on the oxygen. Well, one way to collect oxygen gas is in a water trap, right? So you just shunt that gas over into this bottle. If you want to measure the volume, of course, you'd need a graduated cylinder upside down would be a good choice. And then it'll capture the gas. But the problem is water has a vapor pressure of its own. It forms gaseous water molecules in this space. So you don't have just oxygen gas up there. You also have water vapor. So how do you get around that? Well, fortunately, the vapor pressure is known for water based on the temperature. And you can go to a table and just look it up. What's the pressure of water vapor in a closed space over a pool of water in that headspace? If the temperature is a certain value. Okay, so there I balanced the equation. So in this case, the pressure in that container, let's see, the total pressure would be equal to the pressure of oxygen plus the pressure of water vapor. Okay? You can measure the total pressure easy in that container. Let's back up. What is the pressure in there? Well, what's holding it up? Atmospheric pressure, right? Atmospheric pressure is holding it up. If we adjust the level of this to be equal to the level of the water outside, then the pressure inside the vessel is atmospheric pressure, right? And then we measure the volume after that. So this would be 1 atmosphere. All right, now let's go back. What is the pressure of water in that vessel? Well, it depends on the temperature, right? We didn't say what the temperature was. Let's just say it's standard, 25 degrees in the laboratory. 23.756 torr. So what would this have to be? 760 torr. So the pressure of oxygen that we trapped is this one minus that one. Okay, so now we do know the pressure of oxygen trapped in that vessel. All right, if we know the pressure, right? We know the temperature. We can measure the volume. Now we can calculate the number of moles of oxygen in that container. Okay. Let's see, how are we doing on time? A little after 11. Okay, we got time. Might even be able to finish today. Let's see. Let's use Dalton's law of partial pressure to solve another hypothetical problem. Okay, suppose we have two vessels connected to one another by this is called a stopcock. It's a valve. One of them is a large volume and the other one is a smaller volume. Okay. This one is at a pressure of 2 atmospheres and a volume of 9 liters. This one, however, is at 3 atmospheres and a volume of only 3 liters. Okay? We want to know, and the gas is helium. Actually, it doesn't matter, really. We want to know what's the pressure, the total pressure, after you open the valve. And the temperature is constant at 45 degrees Celsius. So we don't have to worry about the temperature. All right, let's look at this qualitatively first. What do you think the pressure is going to be? Which way are the gases going to move when you open that valve? This one is at 3 atmospheres and this one's at 2 atmospheres. I'd say the 3 atmosphere pressure is going to move toward the 2 until equalized. So the total pressure is going to be somewhere between 2 atmospheres and 3 atmospheres, right? Now, let's calculate what that is. Let's see, I want to see if I've actually done that. Yeah, okay, the next slide. Okay, so the way to solve this problem is to think of it in terms of partial pressures. What would be the pressure if you say that's a vacuum? There's no gas over there. Then this one, when you open the valve, will expand in that space and then equalize. So to be before is pressure volume, and then after pressure volume. You know the volume, right? 9 liters plus 3 is 12 liters. So the first one, this side, would be the initial pressure is 2, and the initial volume is 9. What's the final pressure? That's the question. And the final volume is equal to 9 plus 3. So now we have a before and after with Boyle's law. We can solve for the final pressure if we only consider this gas into a new volume. Then you go over here and treat this one like that's the vacuum. So the initial pressure over here is 3 atmospheres. And the initial volume is 3 liters. The final pressure would be something different, and the final volume would be the same. Okay? Now, how does that help us? Well, consider them as partial pressures. The partial pressure in this first scenario is due to that gas. it gives you a pressure from that gas. And then this one gives you a pressure from that gas. The total is the sum of the two. That's Dalton's law. So if we do that calculation, for the left side, we find that the pressure would be 1.5 atmospheres from this gas alone into a new volume. Then we do the same thing for the other one. And that pressure is 0.75 atmospheres from this gas into the new volume. So the total of those two is the total pressure, 2.25 atmospheres. And that agrees with our qualitative assessment, where the pressure is probably somewhere between 2 and 3. In fact, it's 2.25. Okay, that's how you solve that problem, using both Boyle's law and Dalton's law of partial pressures. Let's see. I'm going to try to finish today, not because I'm in a rush, because we have an extra buffer day, but because I want to cover the material so that when you start to work problems, you'll have all the skills necessary. Oh, okay. Reconnect. That's fine. Okay. Here's another one. Let's see. 27.4 liters of oxygen gas at 25 degrees and 1.3 atmospheres. And 8.5 liters of helium gas at 25 degrees and 2 atmospheres, pumped into a tank with a volume of 5.81 liters at 25 degrees. What's the question? What's the new partial pressure of oxygen? What's the new partial pressure of helium? What's the total pressure? Well, you can calculate the new partial pressure of oxygen based on before this many liters of oxygen under these conditions is pumped into a tank that has a smaller volume at the same temperature. Right? So you're going from, it's pressure volume, Boyle's law. You're going from this pressure to a higher pressure. Why? Because you're pumping the gas from 27 liters into 5.8 liters. So the pressure will go up because the volume went down. Same thing for helium. So we just calculate each one. Right? So there's the pressure of oxygen, the new pressure, right? It went up from 1.3 to 6.13. That's consistent with Boyle's law. Helium, similar calculation, it went up from 2 atmospheres to 2.93. Now what's the total pressure in the tank? Just add them together. 9.06 atmospheres in that tank now. Okay, we've talked about laws up to this point, right? We know that a law is just what happens. It's an observation, a generalization. If we know this set of circumstances, we always get this outcome. But if we want to expand our understanding of the systems, we need to take the blinders off, unbound ourselves. Laws bind you to a specific system, like pressure volume. Can't talk about it in any other terms except pressure volume. until, of course, we get the combined law, and then you sort of expand a little bit, but it's still a law, right? These conditions determine the outcome. But if we try to explain why things happen, you know, why does the pressure increase when the volume decreases? Then the world opens up. You can expand your understanding. And with a theory, which is what I'm talking about, most theories come with models. Some type of model that is a way of visualizing or explaining in mathematical terms, right? There are mathematical models too, explaining in those terms what's happening, and then you can change the model and see what happens to your system. That's the value of a theory. It has a model. All right, for gases, we have this model, or this theory, the kinetic molecular theory of gases. Well, we need a starting point. You know, all theories have certain conditions that must be observed in order for the theory to operate. They call them postulates. Right? These postulates are, one, for gases. Gases consist of tiny particles. They're microscopic, can't see them. They could be atoms, they could be molecules, they could be mixtures of both. The size of the particles are vanishingly small compared to the distance between them. That means most of the volume of a gas is empty space, which means the size of the particles, the individual particles, can be considered insignificant, a zero term in our theory. The fancy word for that is point volume. Remember mathematics? Yeah, point has no dimensions at all. If you connect 2 points with a line, then you have one dimension, length. What if you connect 2 more points? Now you've defined an area. And if you connect in another dimension, you have volume. So height, length, depth gives you volume. In this theory, gases don't have that. They're point volumes, which means zero. No volume for the gas. Now, we know that's not true, but for the purposes of the theory, we're postulating that in the beginning. All right. These particles are all right, there's something left out of this one. Actually, number 1 particle. Gases consist of tiny particles, yes, and there are lots of them, large numbers, but the distance between them is still very large compared to their size. Now, when you've got all these particles in there, and the reason I say there's large numbers of them, there is a large number of them, is for statistical reasons. When we start to analyze or describe an ideal gas in terms of the kinetic molecular theory, we need large numbers of these particles, and they're in random motion, right? The only time that they stop moving is if we're at 0K, absolute zero. That's the only time they stop moving. Anything past that, there's some motion. And at room temperature, there's lots of motion. rapid motion. And the motion is random. Now, why do we have to say random? The reason we say random is because we don't have the computing power to track every one of the particles. Theoretically, if we could track each one and where it's moving at any one time and all of them together, then we could tell how they behave. But we don't have that computing power. Not even the biggest supercomputer can't do it. Besides, we can't visualize them anyway because they're so small. So we have to assume that they're all in random motion. They're colliding with one another. Even though they have no volume, they still have mass. They're colliding with one another, and they're colliding with the walls of the container. That's why we can measure pressure. If they're colliding with the walls of the container, what do when they hit the wall? They transfer force to the wall until it transfers back, right? So when they hit the wall, then they bounce away. Well, in the process, they've exerted a force here that can be measured. And if that force is applied over a specific area, we can measure pressure. So that's why you can measure pressure of a confined gas, because these individual particles are moving. That's what kinetic means. They're in motion. All right. Now, we also have to assume that in addition to the particles being point sources, as no volume, they don't attract or repel each other either. There are no intermolecular forces between them. So they act as if they're all billiard balls. They just bounce off one another. And the collisions are all elastic. What does that mean? That means when they bang into each other, before the collision, they have a certain amount of energy. After the collision, they've got the same amount. There's no loss of energy. So what would an inelastic collision be? An inelastic collision would be like a lump of clay. Then you drop it, it hits the floor, it just stays there, right? Changes shape a little bit. Where did all that energy go, right? It had energy from here, converted into motion until it hit the floor. Where did all that energy go? Converted into heat, right? Friction. When it deformed, it heated up the molecules. But elastic collisions don't do that. All the energy that goes into a collision comes out of it. And that's what we assume for these particles. That's it. There's no attraction, there's no repulsion. Now, we know that's not true. But for the purposes of the kinetic molecular theory, that's one of the assumptions at the beginning. And then if we need to, we modify with reality later. Also, this kinetic energy that's due to motion, right? Each one of these particles has kinetic energy. Oops. That can be calculated. That's not volume, that's velocity. Mass times the velocity squared, take the half of it, that's kinetic energy of each of the individuals. If you take an average of that, of all the kinetic energy of the particles, that translates into the intensive factor we call temperature. Temperature is a measure of the average kinetic energy of all the particles. So that means that as the temperature goes up, the kinetic energy of the particles goes up. Right? They don't all have the same kinetic energy. This is an averaging effect. So why does the pressure go up as the temperature increases? Right? Because the molecules, as the temperature increases, the molecules have more kinetic energy. So kinetic energy, when they smack into the walls, that energy is momentarily transferred into a force against the walls. So the more kinetic energy, the higher the force. So there's the theoretical explanation for why temperature and pressure are related that way. Now, Charles related volume and temperature, but based on the combined gas law, we can also draw a relationship between pressure and temperature. If the pressure is held constant then, and we increase the temperature, then there's a constant opposing force. And if we increase the temperature, that means there's more energy in the molecules, and they're banging against that piston. And only when the volume increases to a point that decreases the number of collisions with the piston, right? If you increase the volume, you're increasing the surface area, right? So the total force that's applied by those molecules that you heated up now is spread over more volume. When it's spread over more volume, you have less force against the piston, and eventually you reach an equilibrium point. So increasing temperature increases the volume to a certain point once you've reestablished the equilibrium. That explains the temperature response of volume. All right, so let's see, I've got all right, we're not going to spend a whole lot of time on this, just a little time. Let's say you have two balloons of the same volume, right? One's got helium, one's got hydrogen. We want to look at each of the following slides and say, all right, how do we explain the conditions for each of the following slides? Well, actually, all we have to do is say, are they different or are they same? All right, same volume, two different gases. Now let's go to the next. The pressure of the gas in the two balloons is what? If you've got the same volume, the pressure should be equal, right? Exactly the same. That was one of the conditions that Avogadro placed on his discussion of gases confined to a specific volume under pressure. They're both at equilibrium with the same atmosphere, which means the pressure times the volume is constant. Volume inside times pressure outside is constant. So if they're both the same volume, they have to be the same pressure. What about the temperatures of the gas in the two balloons are what? Well, they have to be equal too, right? If they were different temperature, then the volume would change because the pressure is the same on both of them. And the number of moles is the same. Okay, there's Charles' law. Numbers of moles, they have to be the same too. That's what Avogadro said. Volume, temperature, pressure the same, moles have to be the same too. All right. Let's see, what about this one? The densities of the gas in the two balloons are what? What is density? Mass per unit volume. Well, we just said the volumes are the same, right? Are the masses the same? If they have the same number of particles, but they're different masses for each particle, then you have different masses. Yeah, different masses for the balloons. Helium should be twice the mass of hydrogen because H2 is about 2 grams per mole and helium is about 4. So those same volumes, helium would be heavier, but the same volume means that the density would be higher for helium. Okay? That's why balloons, dirigibles, or blimps that have helium in them cannot lift the same mass as one filled with hydrogen. Well, that goes to shoot, my mind's gone blank. The concept of buoyancy. So the Hindenburg, before it burned, was able to lift a lot more mass because it used hydrogen and not helium. It used hydrogen because it was forced to, right? The United States, which had the corner on the market of helium, had boycotted Germany. So they had to use hydrogen in their balloons. But they could lift more mass with less hydrogen. The problem is that hydrogen is flammable. The helium is not. Okay. So pressure versus volume at constant temperature. Looks like that. We did that before. Okay. How about volume versus temperature? Right? Volume is 0 when temperature is 0. This is using the Kelvin scale. How about a sketchograph of volume versus moles? Volume is 0 when there are no moles. And then it goes up from there, positive slope. Okay? So with that in mind, what's the mass ratio of neon to argon in these two balloons? We're saying that the volume of neon is twice the volume of argon. That's what volume of neon equals 2 times the volume of argon. Right? So that's what that means. So what's the mass ratio? Well, what is the, if the volumes are that different, we've got twice the neon as we do argon. How many particles, how many moles of neon do we have? We have twice the number of moles of neon. Right? So if we have twice the number of moles and we know the molar mass of each one, we can say something about the ratio. Right? So if we have the number of moles of neon is twice the number of moles of argon, okay, then we need to convert neon into mass. So we have mass per moles. And here we have 2 times argon, mass, moles. That's a different mass, mass neon. But these moles are different. So if we cancel this one and we cancel that one, then the relationship is, what is the molar mass of one? The molar mass of that's argon. Argon. The mass of argon is twice the mass of neon. Right? So this would be this mass no, this mass, would be the same as mass of argon divided by 2. Right? So what happens? Well, if we bring that 2 over there, I don't think this is working out right. It should be divided. They're 1 to 1. I'm not explaining it right. Forget the math. Let's explain it in terms of relationships. If you've got twice the number of particles of neon, but the neons are half the mass of argon, you should have the same mass in each one. Right? It takes half as many argons to make the same mass as neons, which is exactly what you have. Half the number of argon atoms at twice the mass is equal to the number of neon atoms times its mass. So the ratio of the masses is equal, 1 to 1. All right. So let me see. I'm running out of time, but I'm going to see, I got maybe 9 minutes left. I'm going to finish this chapter. You have a sample of nitrogen gas in a container fitted with a piston that contains a pressure of 6 atmospheres. Initially, the gas is at 45 degrees Celsius in a volume of 6 liters. You then cool the gas sample. What would explain the final results? Okay, if you're going to cool, let's go back. So you got, let's put this information on the board. You got a gas with 6 atmosphere pressure. Okay, and it's at a temperature of 45 degrees C. Okay, and a volume of 6 liters. All right. Notice that it's in a cylinder with a movable piston, so the volume can change. So what happens when you cool the gas? Well, the relationship is this. Right? That's equal to a constant. The number of moles stays the same, right? It's confined. So we only have to consider these 3. So what happens to the other 2? The pressure is constant. Look at that. Some mass is pushing down on that piston. So the pressure remains constant because the piston is movable. So the pressure is constant. So now we only have to consider temperature and volume. So if we make the temperature lower, the volume is going to decrease. The pressure of the gas increases? No. The volume of the gas increases? No. The pressure of the gas decreases? Yeah, possibly, because the piston moves. But definitely the volume of the gas decreases. The pressure of the gas, no, the pressure of the gas does not change. The reason being that the piston is movable. So whatever happens to the gas inside, it's under that same pressure the whole time. So the volume of the gas decreases. That's the only thing that changes. Okay, let's see. What gas law should be used? Oh, Let's say a gas sample is cooled to a temperature of 15 degrees. Solve for the new condition, right? If we know the temperature changes, we're basing this upon the previous example. So in this case, Charles' law is what is in effect. Right? We already determined that. And if we do that, we actually put numbers in there and change the temperature, then we can calculate the new volume. Okay. Now, this discussion, I sort of stole my own thunder earlier when we were talking about the ideal gas equation and what is the value of R. In order to determine R, you need to know those four values. And I told you that if pressure is 1 atmosphere and temperature is 0 degrees Celsius, 273 K, and the moles is 1, then the volume is 22.4 liters. That volume is what's known as the molar volume of an ideal gas. 1 mole of gas at 0 degrees and 1 atmosphere pressure will be 22.4 liters. So if you already know the constant here, then you can do that calculation. But what I was doing was I was using the molar volume of the gas to calculate the constant. Right? So this just confirms that the molar volume of a gas is 22.42 liters at standard temperature and pressure. And this standard temperature is 0 degrees Celsius. Okay. Now, here's the usefulness of all of these gas laws together for chemistry stoichiometry. If you have a sample of gas as a volume of this many liters, standard temperature and pressure, how many grams of oxygen are present? What do you need to determine? You need to find out how many moles of oxygen. And if we know the molar volume of oxygen is this, method 1 just says, okay, 22.4 liters is 1 mole, right? So we can calculate the moles and then we can change moles to grams. And that dimensional analysis problem gives us 3.57 grams of oxygen. The other way to do it is use the ideal gas law, right? And if you plug in all the values that you know, you can calculate moles of oxygen, then convert moles to mass. Okay, get the same answer. Now, this one works, the first one works only for standard temperature and pressure, because that's the molar mass under those conditions. If you have different conditions of temperature and pressure, then you have to use the ideal gas law, because it will take into account those differences during the calculation, and you'll get a different number of moles of oxygen. Then you can convert to grams. So in this reaction that I put on the board earlier, zinc hydrochloric acid makes zinc chloride plus hydrogen gas. With that balanced equation, we can take information and answer the question, what volume of hydrogen gas is produced at 25 degrees and 1 atmosphere? 15 grams of zinc reacts with 100 milliliters of 4 molar hydrochloric acid. Right? So we got a balanced equation. We've got amounts of each one, right? 15 grams of zinc 100 milliliters of 4 molar hydrochloric acid, what volume of gas is produced? Remember, you're given exact amounts of each one. So one of them is probably going to be limiting. So you got to find the limiting reactant. Then you can determine how many moles of hydrogen and convert moles into volume. Right? So let's do that. I think we work it out here. Next slide. Yep. So there's your balanced equation. This is how much zinc you're given, this many moles. Remember, you can't go anywhere in a balanced equation unless you got moles. So we got moles of zinc there. There you go. So how much hydrogen can be produced from that zinc? All right. Now you got this many moles of hydrogen chloride. How much hydrogen can be produced from that much HCl? Only 0.2 moles. So the hydrochloric acid runs out and you're left with some zinc in excess. So we use this many moles of hydrogen gas that are actually produced, not this many. The lesser amount are actually produced. There you go. That's your limiting reactant. That's how many moles of hydrogen you can produce. Then we use the ideal gas equation. Pressure times volume equals moles times gas constant times temperature. And solve for volume. So under those conditions, 25 degrees centigrade and 1 atmosphere, you get 4.89 liters of hydrogen. There we've used the gas laws in stoichiometry. Okay, let's see. What have I got here? Oh, why is the plot of Boyle's law curved? Well, I explained that. It's a hyperbola. But scientists don't like curves. Whenever we can get a straight line, we go for it. If we have to transform the data to get a straight line, we'll do it. So that's what we do with Boyle's law. Notice that in order to have a straight line, you need y equals mx plus b, or y equals kx plus b. K is the slope, y is the intercept. Right? How do we transform p times v into a form that will give us a straight line? Notice, okay, we're not dolphin anymore. Notice that if we write this expression that way, what would happen if we put volume on the other side? Right? Or in mathematical terms, multiply or divide both sides by v. That's allowed. So now that one cancels and we get P equals K over V. Another way is K times 1 over V. So notice what that looks like. Y equals mx. So our Y is pressure. Our X is 1 over V. So if you take all your volume measurements and take the inverse of them, then you can plot that and you will get let's see, there you go. If you plot that, well, actually, pressure's Y. If you plot that, you get a straight line with a positive slope. Okay, that's how we transform Boyle's law into a straight line form. Okay? Oops, that's it. So that's, we're only 5 minutes over. That's good. So next, let's see, today's Thursday. Next Tuesday, we'll look at homework in Cengage.